Welcome, students. We want to talk about an impulse force. So, recall again, you had your system of spring, and now you are interested in different kind of functions. G, we said that Laplace transform becomes more interesting when this G is discontinuous. Today, we are going to study about G, where G is an impulse force. Okay. So what are these impulse force? So impulse force is a force of a very large magnitude applied over very small or very short duration. Okay. So this is what impulse is. Like say, think about you have a bell and then you just bang it for a second with a very high force. Yeah. So that is an example of an impulse force. Okay. So the time duration on which it is applied could be even infinitesimally small. Hmm. So the function g of t is an impulse function if it is very large over a small interval of time. Say, let's say the time interval is there is some t naught and you're going t naught minus tau, t naught plus tau. So your function the graph of the function will look like. So it is 0 here, and then it becomes very large here. Okay, so this is very large, all right? So I cannot draw very large here right away. So I just want to point out that this is a very large value. So such a function is called impulse force. Okay. So now let's look at the area under the curve. This is called total impulse. Okay. So total impulse is basically minus infinity to infinity g of t dt. So you're finding area under the curve where, so it will be minus infinity to infinity g of t. Okay. Now, for an impulse force, the value of I should not change for small t. So in particular, for simplicity, just let's take t naught equals to 0 so that we can move it around the y-axis and consider g of t of the following form. So g of t is 1 by 2 tau if your t is between minus tau and tau, and g of t is 0 if absolute value of tau is greater than or equal to 1. So here we have, so what is my total impulse is going to be minus infinity to infinity g of t dt, because that's what the area under the curve is. And then you can see this is going to be minus tau to tau 1 by 2 tau d tau, and so 1 by minus tau tau 1 by 2 tau, and you get dt, my bad, not tau. So we have 1 by 2 tau times t limit from minus tau to tau, and then you substitute, you'll get this is 1. So notice that I is going to be 1, is fixed regardless of tau. Yeah. So now note that the smaller your tau is, the bigger this force is going to be, right? So now consider the limit of this function as as basically as tau goes to 0. So how will it look like? So let's draw. So so when say tau equals to, you have 1, 2. Say if tau equals to 2, you will have from minus, so minus tau to minus, so the function is basically minus tau to tau, it is going to be 1 by 2 tau. So minus 2 to 2, it's going to be 1 by 4. So something of this sort. So this is So this is how your function will look like. Now when tau equals to 1, when tau equals to 1, you will have from 1 and then will go all the way until 2. So this is how the function will look like. Okay. Now, if you let tau goes to 0, you will get a peak like that. So this is as if it goes to what? Infinity, right? So this is how the unit impulse function looks like. In fact, this function is called unit impulse function and is denoted by delta t and also called as Dirac delta function. And now two things are important about this function, namely delta tau equals to 0. Sorry, delta t equals to 0 if t is not 0. And we have integral minus infinity to infinity delta t dt equals to 1. Now, really, I mean, like this kind of functions, I mean, like there is no such function really which satisfies this. In fact, delta, the unit impulse function, is not a function in the usual sense. Okay, so few important remarks. But because it makes sense from the physicsy aspect of it, you can have a function which acts on your system. Say you're ringing the bell, you're hitting the bell with a stick or something, and that time interval, if you hit it once, that time interval could be really, really, really small. So it makes sense to talk about such an object. So first of all, notice that delta t is not a function, is not actually a function. What is it then? It is basically, but it is so-called generalized function. That is, it is extending notion of function in one sense, right? Now note that it's an important tool in applied math. It's an important tool in math and engineering. They can be developed rigorously, but we will skip that here. We will skip it, unfortunately. Okay. So 2, let's go back to delta t, which is a unit impulse function. So delta t, the unit impulse function, at t equals to 0. If the instantaneous force is applied at any t naught, force is applied at arbitrary t naught, then corresponding impulse function is going to be is delta of t minus t naught, right? So it's moving it to t naught. Now let's look at some few key properties of delta. So if you integrate minus infinity to infinity, f of t, delta of t minus t naught is f of t naught. Well, for f a continuous function. Where you can think about f as a continuous function on our of real numbers, or at least on interval surrounding t naught. Okay. So, well, this is going to be limit as tau goes to 0 plus minus infinity to infinity f of t g tau of t dt, right? After all, limit of this is the unit impulse function, so I can write it this way. So this is going to be limit as tau goes to 0 plus, we have, well, how's your g of t defined? G of t at around 0 will be defined as 1 by 2 tau if you're from minus t to minus tau to tau and 0 otherwise. So I will basically, everywhere else is going to be 0, and from t minus t naught minus tau to t naught plus tau f of t dt, right? Now note that g of t, let me just rewrite g tau of t is basically 1 upon 2 tau if you are in the neighborhood of tau. That means if t minus t naught is less than tau, you can also have less than equal to, that's fine, or 0 otherwise. So this is a definition of your g tau, right? Because it's centered at t naught. Okay. So what do we get out of this? So this is going to be, so we need to simplify this now. So as tau goes to 0 plus, we'll have f of t is roughly f of t naught, right? Because it's a continuous function since f is continuous. So for t minus, so in what range though? For t belonging to t minus tau naught, so t naught minus tau and t naught plus tau. Yeah, and this is because f is continuous. So now I can replace in this integral. So the integral becomes, let me call this integral. Well, let's use another notation for this integral, say j. J equals to, so then I can replace f of t by f of t naught. So I'll have limit as tau naught goes to 0 plus t minus this, t naught minus tau, t naught plus tau, f of t naught dt, f of this will come outside, so we'll have f of t naught times t, which is going to be t naught plus tau, t naught minus tau to t naught plus tau, and that is going to be f of t. And what is the, so we get here, we had 1 by 2 tau here outside, we had 1 by 2 tau outside, it's going to be 1 by 2 tau outside. So this is going to be f of t naught 1 by 2 tau. So when you subtract them, you get t naught. So we get 2 tau, and this is limit as tau goes to 0 plus. So let me rewrite this properly here. So we get, this is same as limit as tau goes to 0 plus 1 by 2 tau. F of t naught comes out of integration. You are integrating dt, which is t, from t naught plus. So we have already integrated that. When you subtract, it will be basically 2 tau. And these guys will cancel out. You're left with f of t naught. Okay. Now, all those. Now we want to talk about the Laplace transform of this function, delta t. Now, note that although delta t is not a function, t is not a function. So it's not a function, we have already discussed. It's not a function. The integral above means the integral above facilitates facilitates the definition of Laplace transform. Laplace transform. Let's see how. So Laplace transform. So again, let's talk about Laplace transform of delta of t minus t naught of s. This is going to be 0 to 0 to infinity e to the power minus st delta of t minus t naught dt. Now in this case, your function is basically, in this case, your f of t is what? F of t is, note that f of t in this case is going to be e to the power minus st. So this becomes, from above, it becomes, so I can write it as minus infinity to infinity because it's 0 otherwise, e to the power minus, I can write it as f of t delta of t minus t naught dt. What is my f of t? Where f of t is going to be is e to the power minus st if t is greater than equal to 0 and is 0 otherwise. So in this case, we have, this is same as going to be f of, or this can be written as e to the power minus s of t. So now let's solve the following IVP. We have y double prime plus y prime plus y equals to delta of t minus t naught, y of 0 is 0, y prime of 0 is 0. So first step, take Laplace transform on both sides. So in that case, we'll take s square y of s under usual notation. So this was our notation, right? Minus s of y0 minus y prime of 0 plus s of ys minus y of 0 minus phi times y of s equals to delta of, so Laplace transform of delta of t minus 3 s. So now this will become, these all become 0, right? So what are we left out with? This implies take y of s common, so we are left with s square plus s plus 5 of y of s, and this is going to be equal to, so this is formula 17 of table. So this gives us e to the power minus 3s. Yeah, you can also see it from this perspective here. We have already shown that, but you can use the formula from the table. So therefore, we get y of s equals to e to the power minus 3s upon s square plus s plus 5. Now, so this is, so we need basically this is going to be e to the power minus 3s times h of s. Now we need to compute Laplace inverse of, so what is h of s? So h of s is, so we need to write down h of s in a form we can identify. So your h of s is 1 upon s squared plus s plus 5. This can be already seen as s plus 1 by 2 square, if you complete the square, plus 19 by 4, yeah, which can be seen as 1 by s plus 1 square, half square, plus square root of 19 by 2 square, right? Because we are going to use the sign, right? So therefore we get y of t equals to, what is the Laplace inverse of this guy? Laplace inverse of this guy is going to be u of u3 of t, because of this part here, times h of t, where what is h of t? Where Laplace transform of h of t is your h of s. Yeah, so you want to find Laplace inverse of this guy. So let's compute Laplace inverse of this. So we have Laplace inverse of h of s. So this is what our goal is now, is going to be Laplace inverse of 1 by s plus half square times square root of 19 by 2 square. Now this would have been sine, so recall Laplace inverse of a by, b by s plus a square plus b square is sine of bt e to the power minus at. So we need to get that. So if you compare, we need a factor of b on the top. So what is, so this is going to be same as, I'll multiply top and bottom by square root of 19 by 2, and here square root of 19 by 2. So then this becomes 1 by square root of 19 by 2, so square root of 19, the whole divided by 2 times e to the power minus a is half. So let me write that. A is half minus half, a is half, and b is square root of 19. So we get this, it becomes e to the power t by 2 sine of root 19 by 2. So this is your h of t, and therefore y of t is u3 of t times 2 divided by square root of 19 e to the power. Now we have what? H of t will get here h of t minus 3, right? Because of this thing here. So this is going to be h of t minus 3. So when I write it here, it's going to be e to the power minus 3 by 2 times sine of root 19 by 2 times t minus 3. And there you go. So that's the solution. Now, if you look at the graph, this is how the solution looks like with respect to t. So this is the time at which the impulse is applied. Pulse was applied to system. So the time was here, t equals to 3. And if you see that is correct, I mean, at t equals to 3, you have the impulse function applied, and then you have the following, that before, so this is how the solution looks like: 0 for t less than 3 less than equal to, and then we have 2 by 19 t to the power minus 3 sine of 19 by 2 times t minus 3 if t is greater than equal to 3. Yeah, yeah. So so this is a solution. This is exactly same as your yt. So instead of writing it case by case, it's better to write it as one function. So that's about it. Thank you for your attention.